So it was kind of unavoidable recently to write on digital twins because we were basically forced from all sides to comment on this issue. Everyone basically saw this is going to be the future, and of course it is. But also the feeling was this is going to solve all the problems. Once we have a identical digital copy of the world, and we know how the world works, everything will be fine, but then all those emergency happen. So unfortunately, it's not that easy with digital twins. And since there's ChatGPT, actually, we know that even though this is a very powerful and nice tool, it's making a lot of mistakes. It's lying to us many times. It takes a long time to figure out when this is actually happening. And so if we apply that kind of technology to run the world, there will be mistakes. And by the time we notice there are mistakes, it may be too late. So yeah, we should think of digital twins also perhaps as deep fakes, lookalikes, but not identical models. And in effect, one of the points that has been really largely forgotten about is complexity science. Digital twins work very well for architecture, urban planning, production, supply chains. But when people are involved, there are so many more things that matter. And in many cases, immaterial things. Friendship, trust, and whatever. So this is something that is often not very well represented by those digital twins. So Javi and I have written a book chapter that works out what are the issues with those digital twins when applied to people and society, what is missing and what would have to be added, basically. This paper, I'd also recommend you to have a look at. This is about cities, and of course, cities also involve people. And really, we need to take into account complexity science, the fact that societies and cities are complex. Now, that's not necessarily a bad thing, actually. Oh, this is interesting that age has just disappeared from this slide. I have no idea how that happened. The wonders of digital technology. So I want to give you some examples of where complexity science was really informative to solve some problems. And in particular, there's traffic physics, which help to understand all sorts of congestion patterns and what is going on in traffic based on equations that are inspired by physics. And not only did we get a better understanding of what is going on, we also, based on that new understanding, we came up with new solutions. And why is this not running? Okay, because this is on a different computer. So let's see. No, unfortunately, transferring that file to a different computer just killed that beautiful movie. So what we're showing over there is that on the one hand, we can understand the stop and go traffic forming on freeways many times. But on the other hand, there's also a simple way to get rid of those traffic jams by just slightly changing the interactions between cars, which can be done by traffic assistance systems. And the interesting point over here is that we don't have a traffic center that controls all the cars to coordinate them, but free traffic flow results from self-organization based on the right kind of interactions that would facilitate free traffic flow. Now, the question, of course, is could we transfer this insight to other problems as well? And you would think of urban congestion, and there are noble goals of urban traffic planning, better mobility, less pollution, less noise, less traffic, and all of this. But then this is often the reality, or even this urban gridlock. And besides, there are lots of regulations and control, for better or worse, hard to say. We have taken a new approach, really based on complexity thinking. he basically said, let's reinvent traffic light control. Traffic light control has been basically done by control centers, a dictatorial approach in a democratic society, you know? Is this a good thing? We were interested in, was it possible to come up with an adaptive self-control approach that is suited for complex street networks that can handle traffic disruptions and particular events? And in fact, this has also been implemented. So it's not just theoretical, it's not just happening in a computer model or simulation, but it turns out to be working. And it says more green for everyone, something that seems to be an impossibility, but it just means that we're not wasting green time as much as all the other traffic light control schemes do. It's also good for the environment, by the way. So I'm not arguing for cars here, but I think everyone agrees that congestion is bad, additional streets and additional lanes should be avoided. Can be done with this approach. And here are some papers related to that, if you want to know the details. But everything was inspired actually by pedestrians. So now we're back to pedestrians. Pedestrians have been so inspiring to us. And here you see a bottleneck, and you see oscillatory flows that emerge at that bottleneck. There's no law that enforces it, no traffic light, no police person. It just happens. And so we were wondering, couldn't we learn from this to come up with a new adaptive self-control scheme for traffic flows at intersections? Because intersections, in a sense, are also bottlenecks, just for more different flow directions. And so the idea was, rather than having traffic lights that control traffic flows, we could have traffic flows that control traffic lights. And how well would that work? And as you can see on the right, in fact, if you do that well, then there will be green waves that result just by self-organization. What we need for this is basically a measurement of outflows, but also of inflows. Inflow measurement allows us for a short-term prediction. Green times are adjusted to the number of cars waiting behind the red light that will have to be dissolved, plus those cars that are predicted to join that queue before the queue is dissolved. So that is kind of the basic ingredient. So there's some queuing theory or traffic physics in it, or a conservation law in the sense of cars, that cars don't get lost or don't get produced in the streets. That's what we assume. We have compared different kind of control schemes. One, of course, the classical centralized traffic control by some control center, an authority, traffic authority typically, and that's something like a benevolent dictator approach. You try to get as much data as possible, then try to come up with an optimal control scheme, and then impose it on the city top down. The issue is just that it's an NP-hard optimization problem, so you cannot really do the optimization in real time. You need to simplify. You come up with an optimal control pattern for a typical traffic situation, but that actually never occurs. So we have an optimal scheme for a situation that doesn't exist. And instead, we came up with a control scheme which is not 100% optimal, but say 90 or 95%, but adjust to real traffic situations in the neighborhood, and in such a way that coordination would be possible. So we have a distributed approach over here. That's the second thing, where basically all intersections separately try to minimize travel times, like Homo economicus would do if every intersection was Homo economicus. But there's no explicit coordination imposed on the system. And over here, we add an element which is to clear long queues in order to avoid spillover effects. So that's kind of friendly towards neighboring intersections. And you would think, as this is interrupting travel time minimization, that's probably the worst one. So that should be the best, that's the second best, that's the third best. But in reality, it's actually more the other way around. Red line corresponds to traffic control centers as a function of capacity utilization. You see the queue length increases with more vehicles in the system, but the blue line actually corresponds to the third control scheme that I mentioned before, which was a bottom-up self-organizing scheme. And it's much better. It reduces queue lengths. And that, of course, was done in a computer simulation in a theoretical scenario. And then the question is, how does that actually work in a real world setting? And so we said, let's talk to the city of Dresden. That is where actually the scientific journey began. And they said, we're quite happy with our traffic light control. We just bought a state-of-the-art system. It produces green waves. It actually even adjusts the green waves to traffic flows. And so it cost us a few million, but we were happy. Apart from one thing, like we'd like to prioritize public transportation. And if we do that, basically we interrupt the green waves and then we'll have a monster traffic jam within just a very short time. Like Shlomo would be excited to see all those jam trees, of course, but citizens would be less excited. And so they said, okay, if you think you're smart, here, this is the part of the city that you should be focusing on, like the most messy part of the city, not a square grid at all, very irregular street network, just in the center, and then all those different tram and bus lines cutting through in different ways and messing up things, basically, But we came back and we compared those different schemes based on data that were measured. And above you see actually the state-of-the-art control that imposes clearly the green waves on the system. And below you see also green waves, but a lot less regular, which means it actually adjusts to the traffic flows and the gaps in the flow. And so it's not imposing something, but it's responding to opportunities in a sense. And in fact, this is the result. Public transport could be prioritized. It benefited a lot, but not at the cost of motorized traffic, individual traffic. So they also had some gain, not as big. It was also good for pedestrians and cyclists and for the environment. So, everyone should be happy. And now, of course, a few years have passed. In the meantime, you would ask, so what about AI and machine learning? So couldn't these approaches do a better job without having to do so many complicated calculations? Just let machine learning learn the problem and come up with an optimal solution. And so we've been looking into different kind of control schemes, and analytic plus is basically what I just introduced to you, and it turns out it's doing surprisingly good. In fact, Marcin, who is a PhD student in my team, he has a machine learning background, He was kind of shocked to find out that analytic plus was working so well. And there is a way to combine analytic plus and machine learning that basically benefits both. So that's a hybrid approach. However, it's less so in disrupted systems. And in fact, that's the reality, right? There's an accident here, there's a building site there, there's an event over there. So there are always disruptions in cities. And by the time the machine learning has learned a new situation, there's a new situation. So basically, machine learning is not quick enough in learning, in adapting to the situation, while analytic plus just uses that little information that is really needed to do a good adaptation locally. And so, yeah, it's just better. So in these kind of complex systems that have a lot of variability and little predictability, there are good ways of managing these systems based on self-organization. And so we learned that we cannot control everything top down. Now, the question is, what are the implications of this for our society altogether? Can this principle be extended beyond traffic? And the answer is yes. That is our conviction, based on the experience that we have collected. We have done many projects in the past years, really to work it out, to demonstrate it. This was still a more theoretical comment, build digital democracy, kind of suggesting that we could use collective intelligence for our society and what were conditions to support it or assist it. And we've also done made the contribution to the ETH Policy Challenge. That was a hackathon, and actually our contributions on Empower Polis, Digital Agora, was the first ranked project at that time. We've done a lot more. So I'd like to mention crowdsourcing. Of course, we didn't do OpenStreetMap, but it's a very good example for crowdsourcing. And actually, we do use OpenStreetMap in various projects. Greener, for example, is just a recent project of Sajid. And we've been developing participatory health apps that would actually be protecting privacy, but still give useful aggregated information to people in order to take informed decisions about what they could or should do to protect their health. We've also been working actually with Johannes and Evangelos on an app for more sustainable consumption, which is not trying to impose certain kind of shopping behaviors on people, but is actually trying to suggest products that fit the values of the customers. And in many cases, those values include health, good environmental conditions, and so on. So we don't have to force or trick people. We just need to help them with good information. We've built the Vote app in order to look into different kind of voting rules and what the implications are for the outcomes. We've been working on crowd sensing. The first platform of this kind was called NervousNet. Was a bit sabotaged, I would think, but the idea of kind of running in the Internet of Things as citizen web to some extent is living on in projects such as Finance 4.0. That means a socio-ecological finance system based on multiple currencies that would be based on multiple different kinds of measurements of environmental variables and so on, in order to allow for favorable feedback loops that would drive the system towards a circular and sharing economy eventually. And then we have also been engaged in citizen science, Sajid in particular, and we have created those beautifully looking, I think, air quality sensors, and those are being used to do measurements with the support of citizens. And last but not least, I'd also like to mention the City Olympics or the City Challenges or City Cup that we came up with actually here at the Complexity Science Hub in Vienna, which basically suggested that cities could compete with each other for better solutions for the challenges that humanity is faced with, involving all the different stakeholders. That means on the one hand, of course, politics, governance, media, and so on, but also science, citizens, most of all. So basically allowing everyone to make contributions towards better ideas, better solutions, better implementations. And so we came up with different kinds of disciplines in which the competition would take place, including increasing biking to work and recycling and CO2 compensation and all of this. So the overall idea behind this is localization rather than globalization. So to think global, but to act local and diverse, to experiment, to learn from each other and help each other. And in fact, we have launched this pre-pandemic times. Then the pandemic came, so it did not scale as well as we hoped. But the idea is out, and I think it's unstoppable. And in fact, Jose was really also instrumental for this. You see also India on the map. So we've been demonstrating the idea. And so there are many things we can do to use digital technology, and also digital twins or digital avatars or models of reality of different degree of realism or simplicity to help us come up with better solutions and assist people's decision-making and action for a better world. So be a game changer. We can now bring the best of all systems together: competition, collective intelligence, experimentation, and intelligent design. And all of this can go into those city challenges. Thank you so much. That's it for now.